Hello, this is a video tutorial made by Robotix IIT Kharagpur for participants of the image processing event of Robotix 2013 Seeker. We hope that by the end of this tutorial, participants will have a good idea about how to go about making a robot for this event. Now let's just have a look at the problem statement before proceeding. Design an image processing robot capable of navigating indoors by recognizing and following directions and signs. Now, for any image processing event, the robot has very generally two modules. The first module is the coding part of it, the image processing part of it, and the second module is the hardware. And interfacing between the two finally leads to the robot. We'll be discussing image processing in the latter half of this because that's where the bulk of the challenge lies. While the hardware, which is relatively simple and straightforward, we'll discuss that very quickly right now. What would you think would be necessary for an image processing robot, the hardware part of it? You'd need a camera, obviously, to visualize the environment around it. There'd be a laptop to which the camera would be connected, and that would be doing the image processing. Your image processing code would run on your laptop. You would have a differential drive, simply a chassis, two motors or more, two wheels and a caster wheel, or four wheels accordingly, and on which would be placed the camera. You'd also have a microcontroller placed on a development board that would be responsible for taking instructions from the laptop, and this in turn would send instructions to a motor driver circuit. This motor driver circuit, which consists of two H bridges, this motor driver circuit would then send necessary instruction in the form of electrical currents to the motor based on the instructions it's received from the microcontroller. Let's just have a quick look at a block diagram which will help us understand. Yes, here. So if you have a look, this is just a block representation of what your robot or the connections might be, what it might look like. So here you have the differential drive chassis. We hope all of you have an idea of what a differential drive is, how it works, how to make one. Even if you don't, shortly we'll be telling you links, not only how to make a differential drive, but for every other module that we discuss here. So here is the chassis, just a symbolic representation. Here are the wheels. On the chassis, probably you would have the development board, which would contain the microcontroller. You'd have the motor driver, you'd have the camera, and the camera would be connected to the laptop. Now the laptop, you might keep it on the chassis if it's really large, but then even if it's not, fear not, we'll be having USB extender cables, so you can easily connect your camera to your laptop while you can sit comfortably outside the arena and let the robot move with the camera on it. And of course there'd be a power supply to power everything on the robot, because obviously it won't work without power. Now for this, we at Robotix will be providing you with a standard 220 volt AC source. Now you could choose to go completely wireless in terms of your robot and have a battery, or you could have an adapter, or you could have a transformer rectifier, which takes the latter two, of course, will be taking input from the 220 volt source, which we will be providing you. Please note that we will not be providing any other sources of power, so make sure that you have the prerequisites with you. Now the motor driver, as you can always have a look at the pin diagram of the motor driver. In fact, let's just have a look. If you go to our event tutorial page and follow the link from microcontrollers, you will go to the part of the microcontroller followed by the motor driver. This contains a circuit diagram of the motor driver, what the connections need to be made, and how you can use that for whatever you're doing. So that's the motor driver now, and the microcontroller also, the details are also there on that page itself. We won't be needing much of microcontroller programming for this. If you simply follow the module that we will discuss shortly, you'll be able to do that. You'll have the camera, of course, that's connected to the laptop, that's been discussed. That does not need to be powered separately by a power supply, because it will be connected to the laptop. If you want, you may also think of having a wireless camera. That is, if you have a smartphone, you can always download an app called SmartCam, which allows it to interface with your laptop and take feed directly from there. And the power supply will also be giving 5 volt to the motor driver. If you look at the circuit, 12 volt which is needed for the motors, and will again give 5 volt to the development board, which is needed for the running of the microcontroller. Now the development board will be connected again to the motor driver. You may see our tutorials for the standard connections, because the instructions, the inputs to the motor driver will be sent from the development board. And the laptop will again be connected to the development board. This will be through either wired or wireless communication, depending on which module you prefer to use. Finally, the motor driver will be connected to the two motors, because one motor driver, as we all know, can control two independent motors independently. So this is basically the block diagram that we are talking about. Now if you have trouble with any of single of the modules, any of the single modules that we discussed, feel free to visit our tutorials page. For mechanical, you can for the differential drive, that is, you can go to drive mechanisms here, and if we follow that, you'll see we come to a link which describes how to make a differential drive, how it works, and all the details of that very simply. If you have a problem with microcontrollers, you can go to AVR and line follower, because line follower is a very simple implementation of a microcontroller. As shown before, you have the microcontroller followed by the motor driver and how to connect the two. And regarding wired and wireless communication, this tutorial for serial communication comprehensively covers how to do that using an AVR microcontroller. Basically, the code that needs to be burnt onto the microcontroller is here. Also, the program that needs, or the snippet of code that needs to be used from Visual Studio, and 3 files you need to download. What happens is, if you have a look at a UART tutorial, that's here, if you follow the mouse pointer here, it will describe to you how exactly wireless communication happens with an AVR microcontroller, right? And then if you follow our serial communication tutorial here, you can find out what is the sequence of steps you need to follow to implement that. So now, assuming that all of these modules are done properly, what you will end up with, you'll end up with a differential drive working properly, that when sent certain characters from the terminal, from the laptop, moves in particular directions because of the microcontroller and how it controls the robot. And till this point, it's mostly hardware interfacing and a bit of AVR coding. No, there's no image processing till this part. Now, how will we connect this to our image processing? What's going to happen is, you're going to write your image processing code either in Visual Studio or some other IDE development environment, and from here, the program that runs from here is going to send a certain character through serial communication, again for which we have included sample code here, how that's done. That character, when sent to the microcontroller, when the microcontroller receives the character, the microcontroller's code has been burnt in such a manner that based on certain characters it receives, it instructs the motor driver to make the motors move in a particular direction. A very popular combination, and the one most widely used, is WASD. For most video games, you must have seen that W makes the character move forward, A left, S backwards, and D right. And we can use Q for stopping. So similarly, if you burn your code such that if the character received is W, the motor drivers make the motors move forward in whatever orientation you've decided it. Similarly, for A, it makes it move left, for S, it makes it move backward, for D, it makes it move right, and for Q, or any other character for that matter, it stops. Now, these are the 5 kinds of motion that a differential drive can do. And if your code is burnt like this, then when you send a certain character from Visual Studio, then the motor driver, the motors will move accordingly, and the chassis will move accordingly. So once this entire segment is done, your hardware part is pretty much ready. And again, you can refer to any of our tutorials or ask us any queries on the forum anytime if you have any problems in dealing with this. Okay. Now comes the real difficulty, where the real difficulty starts coming in. That's the image processing part of the event. So let's have a look at the sample arena and see what you need to do. So here I have opened the 3D model of the round 0 arena. Okay, if you have a look, it's something like this. There's a sample robot here to show what your robot might be doing. This is what your robot might look like. I mean, this is of course a very crude diagram, but you might have a chassis here, you might have a camera here, your development board, your microcontroller, your circuits, everything here, your 2 motors here, and this is how it will be moving about. From the robot's view, it's going to look something like this. Now, you might think, what exactly are you supposed to do to move on from here? Before we proceed, we will assume that the image processing modules in the image processing tutorial set that's available here, we'll assume that you have gone through all of these, you've implemented all of these, because each and every one of these modules is needed for attacking the problem statement. You need to know how to convert to grayscale, you need to know how to use binary images, you need to know how to detect edges, how to reduce noise, how to detect color, how to detect blobs, and the shape detection part of it too, which we'll discuss in detail here, since that is the main part of this event, that's detecting and recognizing shapes. Now, before we get to the implementation, let's have a quick discussion on how you would approach, say for example, following this lane, which is the first part of this event, right? You have to follow a corridor, reach to the end, and then once you reach the end, you have to process the sign and turn. But before you follow the corridor, and before you reach the sign for that matter, you have to follow the corridor properly. Now you might assume that since you'll be starting in the middle, that you can just go straight till you see a sign, but then that won't always help you, because at a later point, once you make a turn, you might not make a perfect turn, right? So you need to be able to find a generalized way of noticing how you are going to follow this lane. And this is a kind of problem statement called lane following in image processing robotics. Okay, lane following. So so what we need some way to be able to understand these lines. If you follow the cursor, the pointer shaped like a hand, we need some way to be able to understand these lines and then to be able to process them. So assuming your image processing code has been done properly, I'll just show you a sample bit of code here which reduces that image I just showed you to a simple. Let's just build this. Just wait for it to build. Basically what we'll be doing is we'll be reducing this image, which presumably your robot will have just at the moment it starts. We'll be reducing that image to something that is more easily processed, and then we'll be discussing a method as to how we can analyze this to help our robot follow the. Okay, so the code is built, and let's just run it and we'll see what I'm talking about in a minute. Now these are code modules that you'll have to make, and if you follow our tutorials, you'll understand properly, and you'll be able to understand what's exactly going on here. So what we've done is we've just taken a static image of that screenshot. You can imagine that when your robot first starts, this is possibly the first thing it will see when it starts at the beginning of the corridor. There will be more noise in this image, of course, which is why we encourage you to use noise reduction and to find out how to reduce the noise. But assuming this, we can, after applying noise reduction sufficiently and canny edge detection, we can do something like this. As you see here, this is canny edge detection. Now we'll be doing some thresholding, and we'll see that this has been reduced to a great extent. So now all of that entire image was reduced to something like this, and we can imagine that most of the corridors at least will look something of this sort. There will be two lines going in a diagonal manner, slightly diagonal manner, and a sort of horizon at the end. Let's take a clearer look at this image so that we can have this is a clearer look. Now how would one analyze something like this? Well, for starters, we wouldn't want the upper part of the image to disturb us just yet. At the end of the corridor, of course, we will be needing to recognize the arrow, but right now we just want to focus on the lane. So what you could do is, again, this is all assuming you've gone through the image processing tutorials, you know how IP works. You can sort of choose to exclude maybe the top, certain portion of the top of the image, and focus only on the bottom portion of the image. You could do something like that. And now what will you do with that? Let's assume that you have excluded the top portion of the image somehow, and that this entire portion is cut off, and you're only dealing with these two lines here, which go on to some extent. Then what would you do then? Let's just exit this and discuss the module. So for that, we will study a module known as Hough Transform for lines. Again, there are very detailed tutorials found both on our website and on the web in general. Simply speaking, the Hough Transform algorithm works on the principle of transforming a line in the XY plane to something in another plane. So let's have a look at a simple line in the XY plane. This. Okay, so this is a line in the XY. This is Y, this is X. What the Hough Transform does is, at this point of time, let's say you did your edge detection. At that point of time, it will be very difficult for you to properly calculate a slope of that line, to properly calculate the nature of that line in the image, right? Because it's a 2D array, it's a discrete array, and you won't exactly be able to find out where a line ends and where another begins. So with the line remaining in the XY plane as it does in an image, it will be difficult for you to analyze it, which is why we prefer to transform it into the rho theta plane. Okay, once again, please read the literature on Hough line transform. It's a simple but very powerful method which will allow you to analyze lines very clearly. We use the rho theta plane, where rho is obviously the perpendicular distance of the line from the origin, with some point defined as the origin, and theta is the slope between the x-axis or whatever axis you choose and the perpendicular to that line. We convert it to this plane because we find it, we're going to see in a minute how it's more useful. Now, in this case, assuming you have done proper image processing so that only pixels that are part of edges appear as white pixels in your image, like at the end of canny edge detection, we'll run a Hough line transform on that image to find out what the slopes are of the lines, that in the image under consideration. Now, assuming you neglected the top portion of the image as we discussed, let's just run the Visual Studio program again. Assuming, let's just clear this out. Assuming you ignored the top portion, you'll only be left with this line if you follow the pointer, a line like this and a line like this. And if you found some means to maybe calculate the slopes of these two lines from some predefined point in the origin, you would see that this would, at the center point, perhaps at somewhere near the center point, the sum of the slope of this and this, the algebraic sum, would be near 0. So a good way of testing if you're at the middle of the line or middle of the corridor or not is whether the slopes of the sum of the slopes of the two lines is near about 0. And you'll find that if you can do your Hough transform properly and you add the slopes and you do this and you always try to keep moving to such a point such that the sum of the slopes is 0, so that if at a particular angle, let's go to this, if say at an angle like this, okay, this line and this line, the sum of these slopes would not be 0, it would be non-zero. Now finding out whatever the sign of this would be, as in the algebraic sign, if you can correspondingly make your robot turn in the other direction, send the character that forces your robot to turn the other direction till such time that the sum of the slopes becomes nearer 0, then that would be one way of correcting the position of your robot. And you can keep doing this, and knowing when it is in the middle, you can just keep moving forward and always adjusting yourself and moving forward, and so that this would form a means of lane following. Okay, so how do we get this row and this, how do you get the slope rather? That is with the algorithm of Hough transform. Let's just have a look. This is in general a simple way. We transform the image to from an xy to an r theta image. Okay, we then how should I say, we traverse each white pixel of that image, assuming that each white pixel is a member of some line or some curve even for that matter, and having found each edge pixel, we iterate theta from minus 90 to 90 because that's the range theta can be part of in appropriate steps, and we get each possible value of r from x cos theta plus y sin theta, since that is the parametric representation of the line. And in an accumulator array, which is an array of r and theta basically, we increment the value of that, where r corresponds to rows, I should say, corresponds to rows, and theta corresponds to the angle. We increment the corresponding location by 1. And at the end, we'll find that if we analyze this accumulator array, it's called the accumulator array, and we find where the local maxima are, we'll find that those points, those points of r rho comma theta are lines in the image. They may not be lines extending throughout the entire image, they may be lines for a particular segment of the image only. This method only returns to us the slopes and the perpendicular distance. It does not tell us exactly which segment, line segment is there in the actual image, but you'll find that that's actually enough for our purpose, because if the image that we are using has only this line and this line, these are the only two lines, we only need to sum their slopes, and we found out how we can get the slopes from this method to get the center point of the line, and always try to make our robot move towards that center point. So that's that, and that very simply is a way by which you can implement lane following. After the end of this discussion, you will see a video tutorial, or another tutorial, video demonstration of a robot that is actually doing lane following of a nature similar to this, not exactly but similar to this, and to show you exactly how this would be demonstrated in real life. And so you can see that it does actually work, and that robot uses the exact same algorithm we described here. Of course, it's upon your programming skill as to how you can tune it, how you can use the image processing to fine tune the image and to test it properly so that you can get a good response. So that's the lane following part of it done. The second part is another tricky part, and that is this. Once you've approached the corridor and say now at this point of time the green arrow becomes more and more prominent. If you've read the rules, you know that a green arrow means a turn is allowed in the direction that the arrow is pointing. So what you can do is you can always keep an eye, and the colors that will approach at the end of a corridor can only be red or green. all the signs that we have shown they can only be red or green and nothing else. Just to be sure, let's have a look in case you are doubtful at this arena tab. Yeah, left, right, turn, dead end, stop. These 6 signs in round 0 that can appear there will only be green or red. So you can always check if there's a green or red blob appearing in your sights, appearing quite prominently in the sights of the robot. And at this point of time you can stop your lane detection, because you see there's one line here but there's no longer another line detected. So maybe in your code, once you find out that 2 lines are no longer detected, assuming you ignore the top half, you can only find, if you find only one line, only one major maxima, that means it's time to make a turn or to do something of that sort. Now at this point of time you'll have something like this, your robot will be staring at something like this. And how do we analyze this? Let us first again check this code, a new set of code. Just give me 1 second, just comment out this old code. You can of course combine everything in your code when you finally do it. That's what you'll have to do. We are keeping 2 separate modules for convenience. Let's build this solution. Yeah, so essentially while it builds, let's just have a look. We will want to detect this color, get an arrow where with white suppose being the color of interest, the arrow will be white, and then we're going to analyze that blob, that arrow, and find out which direction it's pointed to or what it's telling us to do. Now bear in mind that you will know exactly whether this color is green or red or not, so you'll know exactly what category of sign it could be and what kind of sign it could be, so you can narrow down your choices there. So let's just run this and see what happens. You see, this is a screenshot of that. Now assuming you've done your thresholding properly, one way to do it is we can use the callback function. Have a look at the callback tutorial. Click on the arrow and get the hue saturation value readings, and now we just change the tolerance. Hue saturation value of course is a very powerful means of color detection. Now see the image starts filling out. Now it's filled out. So the entire image that we just saw has been reduced to just one big white blob, and everything else has been blanked out. Now when you have this, you can proceed easily. Let's do canny edge detection on this image, and now you get something like this. Now at this point of time, there are multiple things you could do. We are not going to be giving you exact instructions. This is for you to test and find out, but suggestions could be, you could find the nature of these slopes, knowing that a particular kind of slope, set of slopes means that it's pointing to the right. This rectangle will be common for both a left and a right arrow, but these slopes may not be so common. If you have a sign, let's have a look at the arenas. If you have the stop sign, you can apply some other kind of canny edge detection and apply some other combination of slopes. The same goes for a dead end. And again, knowing the color, keeping in mind the color, you can also find out whether what exactly is the category of signs that you need. Will it be a sign allowing you to do a particular thing or a sign disallowing a particular thing? And once you have done all of this, you will send the appropriate instructions to your robot, make it start turning, and keep turning until you find yourself, if it's an arrow of course, keep turning until you find yourself at the center of the next corridor, again by using Hough Transform, and then you can move on. Okay, so for this shape, you may find many shape detection modules of code online also. Arrow detection should also be available. You can use your own. You can use contours, corners, for example, counting the number of corners. You can divide this into 2 separate blobs, maybe the rectangular blob and the triangular blob, and compare the centers of coordinates, the centroids I should say, of the rectangular blob and the triangular blob, and their relative position would tell you which direction the arrow is pointing. So there are numerous methods that you can utilize to do this and solve this problem statement. So we won't be spending much more time on this. I think that's the essence of the image processing part, and in general I think the various modules have been covered here. How to maneuver, how to make your way about the corridor, how to make a turn, and then keep turning, something like this, keep turning till you reach the center, and then move on, and then of course when you reach the end, and when you see this sign, you stop. Regarding the other, so this will all cover everything you'll need to do between round 0 and 1 and most of round 2. The only other element is the end of round 2, the final room of round 2, where at the end you'll approach a corridor which looks something like this. Again, we won't give you any other explicit instructions as to what to do. This is a challenge you'll have to figure out, but once you've noticed this, You have to keep turning, move into the room, scan the entire room, find the shapes pasted on all of the walls of the room, and move to the corresponding exit zone and stay inside the exit zone to complete the event. Now we have two small video demonstrations for you that will come just as soon as this discussion is ended. The first will be of a lane follower, I should say. It was made at a workshop in IIT Kharagpur a few weeks ago. This was a lane follower that was implemented using a similar algorithm to the one I described. It's following a lane on a sheet of paper, but essentially the problem statement is similar. Once you've done your edge detection, it's similar to a seeker. The second video demonstration is a small subpart of this last set of the problem statement, or the last module of the problem statement of seeker as a shape detection. It shows a robot following or detecting a circle plastered on a box, detecting it and following it wherever it's going for a short period of time. And we feel that once you have a look at these demonstrations, you'll understand that this is certainly very doable. This can be achieved, and if you simply apply the modules of image processing that we've discussed, both in the tutorials and in this particular event tutorial, we feel you'll be able to make a robot for seeker. With that concludes the tutorial. All the best. Here are the demonstrations, and we hope to see you here in February. Thank you.